full screen. No.
So let's see if that does the trick. Do you see it full screen now?
Black.
Not yet, but wait,
Black.
wait.
You see the number one. Oh, no,
Now
yes.
it's perfect.
Now, okay, great. All right, so the only thing is I cannot see if I can go forward and backwards in my presentation. So that's the issue now. Okay, so yes, it's working. So yes, let me start by apologizing. I changed a little bit the topic, and especially apologize to Gerardo because he had to pronounce all these long words. I'm not really focusing on that. I'm focusing on the last part of the abstract of what that I sent, which is on parent stability, mass gap, binary black hole formation. And in particular, I want to talk about hypercritical accretion during common envelope in massive triple systems. So let me first talk a little bit about what this parent stability supernova mass gap is. So when you have a very massive stars of around 140 solar masses, when you reach the oxygen and carbon burning stage in the core of the star, you start producing very high energy photons, and these photons can split into electron-positron pairs. I'm not sure if someone left their microphone on.
Oh, is it you? Ah, Gerardo.
Yeah.
I can only hear
I muted the microphone.
Okay. So yes, these photons then being so energetic split into electron-positron pairs, and this causes the pressure to drop inside the core. So when the pressure drops, the core collapses and it begins thermonuclear oxygen burning runaway, which makes the star explode, leaving behind no compact object. So neither a black hole, neutron star, nothing. This is known as a parent stability supernova. If you drop below 140 solar masses, then this process also happens when you produce the carbon oxygen core. What you actually produce, it's much less violent. What you actually get are pulsations, and these pulsations lose a lot of the mass from the star, and what you end up producing are much less massive black holes than you would have otherwise. And this is what you can see, for example, in the plot on the right-hand side from a study by Farmer et al. So basically what you're ending up is with black holes, which tend to be somewhere between 40 and 50 solar masses. So basically what stellar evolution theory predicts is that there should be a gap between 50 and about 140 solar masses where there are no black holes. So you could have larger than 140 because those stars will eventually just collapse and leave a very, very massive black hole, or stars which started below these 140 solar masses will produce 50 solar masses and less for your black holes. So, however, when you are dealing with black holes, you are always having these issues. For example, the last decade before gravitational waves became a thing, for example, people were finding some black holes which seemed to be around 20 solar masses, and everyone else was like, oh, your measurements must be wrong. The maximum is around 15 solar masses. And of course, then the first gravitational wave that was discovered, this 1509-14, showed 230 plus solar masses black holes colliding. So of course, you predict this mass gap, and then you have this gravitational wave 1905-21, where you find that the two merging black holes had 86 and 65 solar masses. So, and they formed 142 solar mass black holes. So it was interesting to see if you find the first intermediate mass black hole during its formation, but you also find these two black holes in the middle of the parent stability mass gap. So what's going on with this? How can you form these black holes? I will not talk too much about the spins, but I just want to point out that there's a lot of debate in the community about whether models like the one I will present could form different kind of spins which have been found. And actually, this model allows to produce basically anything you want. So it's not impossible with our model. If anyone has questions about the spins, I can discuss that at the end. So what are the ingredients? Basically, the first thing we'll need to look at is hypercritical accretion. When you have a black hole or a neutron star or any other object, most of the time you talk about Bondi accretion, which means spherically symmetric accretion, basically no pressure around. And that leads you to the Eddington limit for accretion. Basically, photons try to go out through the same region where you're accreting. They produce pressure, they limit the amount of mass that you can accrete. However, in most binaries and multiple systems, what you have is usually accretion by mass transfer. This may be by filling Roche laws or a common envelope or other more exotic kinds of mass transfer. And this is not Bondi accretion. This is perhaps closer to Bondi-Hoyle-Littleton, which breaks spherical symmetry. So basically you have something closer to an accretion disk. So you can accrete as much as you want above Eddington limit if you want through the disk and radiate all the photons through the polar regions. So this allows you to accrete much higher, at much higher rates than what you would have with an Eddington limit model. So this is much more apt, for example, for what's happening in binaries where you have a black hole, which is accreting material from the companion. You can go up to 3,000 times Eddington limit without much issues. And if you go even higher than that, the accretion disk will become so hot that it will start producing neutrinos. And then these neutrinos will be the ones that are radiated, and you can go much higher than that. For example, a supernova during core collapse, we have 16 orders of magnitude above Bondi accretion, and that in that case it's actually spherical accretion. However, the limit is so the new limit in that case will be Eddington limit, but for neutrinos, and that's about 16 orders of magnitude higher than for photons. So what do we do with this? So basically, as I mentioned, we have cylindrical accretion. You're throwing all the outflow through the polar regions. All the accretion is going on through the disk. So you get this super Eddington accretion, which occurs up to 3,000 times Eddington. And if you go beyond that, even if you start having Bondi accretion, since now you're producing neutrinos, you can go much higher. So what's going on in a binary when you transfer material? Well, this is at the bottom, you see this ugly equation for Bondi-Hoyle-Littleton accretion. On the right-hand side, we have a simplified version, which tells you that you can get to around 10 to the -5 solar masses of accretion easily. Once you consider that we'll be accreting onto 50 solar mass black holes, and the orbital velocity of these black holes, or the velocity with respect to the medium, will be around 10 to the 7 centimeters per second, which is more than 10 times the sound speed. That's why you can forget about that from the original equation. So basically, that's the first ingredient that we need: hypercritical accretion onto black holes when you have a common envelope or when you have mass transfer. We have shown actually in a number of papers that this is actually possible. On the left top side, you see our first paper, and we're finding there that you can have around 10 to the -7 solar masses per second onto a neutron star or a black hole. On that one, we were also even launching jets through the polar regions. On our second paper, we decided to, which is the one on the next plot, right below the first one, we decided to make the jets self-regulated. So basically, depends on how much you accrete, how bright the jet becomes. So this interferes a little bit with the accretion, of course. We have higher luminosities, but that all makes also the jet become less luminous. So accretion increases again, and you get this modulation. And it's around the same rate as we had found in the first paper. For the third paper, which you see in the plot in the center, we also decided, well, our experiment is a wind tunnel. So in real life, what we'll have is a black hole inside another star, and it's rotating. So you have Coriolis and all these other forces. So we decided to include those as well. And yes, the accretion rate usually is about 1/10 of Bondi-Hoyle-Littleton, which is many orders, so like 10 million times Bondi. So it's quite large. And on the right-hand side panel, you can see that even in our models, we can start forming accretion disks. You have the Keplerian velocity, and where you see the red rings, you are starting to form an accretion disk at that place, which is around 10 to the 11 centimeters, so a little bit larger than the radius of the sun, but the accretor is still a small black hole in the center. So it looks like the jets should come out from these disks, no problem. Now, the second ingredient is we will need a common envelope within a triple system. We need very large black holes. Even originally, they will be above 40 solar masses. So how likely is it to have a triple star or a triple system like what we need? So if you look at the paper by Mo and Di Stefano from 2017, they find that if you are starting with stars which are above 10 solar masses, basically everything that you see will be in triples, binaries, and if you go above 20 or 30, even quadruple stars will dominate the formation of those stars. So yes, it's not impossible to have triple systems or even quadruple systems with very massive stars. Actually, it's more likely. So that's in our favor. And the other important thing is a study by Comfort and Isert, where they find that if they put a binary in a common envelope with a third star, the accretion rate will be very similar to Bondi-Hoyle-Littleton. So we were finding about accretion rates which are about 1/10 of Bondi-Hoyle-Littleton. What they find is that if you have a binary, then accretion rate will be onto the binary will be very similar to what we would have if it were a single star. It may drop to half of what we are finding, but not much more than that. This is regardless of whether the binary is very tight, so you can treat it almost like a point mass, or it's very wide, so you can treat it as two point masses. The middle range where you cannot make these assumptions, it's a little bit trickier, and that's why they have lots of simulations. But it seems to work with accretion rates which are similar as well. And this is also regardless of the inclination of the orbital of the plane of the binary with respect to the common envelope. So that's our second ingredient. And the third ingredient we need is an efficient mass transfer mode, which we have called a common envelope Rochlov overflow. So this is very similar to what was found in 2007 in a paper by Shasreen Mohammed. And what she finds there is that if you have a star which is close to filling its Rochlov, then its wind becomes kind of focused and goes through Lagrange one and can be accreted with large efficiency onto the companion. So in our case, what we'll have is a binary, and this binary will be the one that when you start having transfer between the two stars in the binary, you will lose some mass, and this mass can be captured by the tertiary star. Some more experiments on this regard were done by Elmela, much more recent in 2019, and in systems which are closer to what we need. So Mohammed did this for Myra systems. Elmela did this for high mass X-ray binaries. He finds 20% efficiencies at the maximum, whereas Shasreen found something like 70 for her maximum. But in our case, we might even be more efficient than these limits, because we have a binary. The binary is losing material. The escape velocity of the binary is smaller than the escape velocity for the triple. So the triple star can still capture a lot of this material. And also you may have even some fallback and form a circumbinary disk, and this material can further be captured by the tertiary star. So this mechanism can be reasonably efficient. So the secret recipe for producing these very large, massive black holes within the peri-instability mass gap, we shouldn't find massive black holes, is the following. So we will mix hypercritical accretion, a triple system, and this efficient common envelope Roche-Love overflow mass gently. So what we did in this paper, and I think I forgot to mention that I'm collaborating with Alejandro Viña, Fabio De Colle, and Diego Lopez Camara, who are also here, not Alejandro, but the other two. So what we're doing is we're taking one of these stellar evolution codes, in this case, Compass, and we take a binary. We cannot simulate the triple system, unfortunately, so we take the inner binary and start with two stars, 120 solar mass star and an 80 solar mass star. After about 3.5 million years, the primary star goes into the red supergiant. It fills its Roche-Love, transfers mass to the companion. The companion mass increases by about 30 solar masses, whereas the other one drops to below 50 solar masses. And a few, like about 1 million years later, it explodes. When the mass transfer occurs, as you can see on the right-hand panel, the secondary star, the one in orange, gets recycled, so it rejuvenates and gets, instead of only about 500,000 years of extra life from what the primary has, it gets about 1 million years. But it also finally becomes a red supergiant, expands, produces a common envelope, and you can see also that there's a lot of mass loss from this system. The system started with nearly 200 solar masses, and it loses more than 100. This is material that's available to be captured by the tertiary star, and that's basically what we need. The tertiary star will be probably a 40 solar mass star, which captures some 80 solar masses, maybe 60 solar masses, and will later bring it back when it goes red supergiant into the binary black hole. So that's basically what we do with the model. From the calculations of what can be accreted into binaries during a common envelope, we can see that if we start, if you look at the black solid line over here, you see that we need to start with a 40 solar mass secondary black hole and a 45 solar mass primary black hole. And they will accrete between the two of them about 65 solar masses. And of course, they will split this mass. The first one will accrete about 40 solar masses, where the secondary will accrete 25 solar masses. This is from the calculation of Comfort and Isert that I was mentioning. And given the very large mass of these black holes, you only need about a couple of weeks in a common envelope to achieve this at a fraction, about a 10% or 10% or 1% of Bondi-Hoyle. You could achieve this in a couple of weeks, maybe a month, and bring this black holes which were originally born with 40 and 45 solar masses to 85 and 65 solar masses, which is what we observed in this system, in the system that merged and produced GW 1905-21. So basically, that's what we have. There's several other candidates for this kind of scenarios among the gravitational wave sources that LIGO has found. I have compiled here about a dozen of them. There's a few other ones which could make the cut. They are above 40 solar masses for the primary, so those could be benefited by this kind of accretion. But the ones that I've included here are above 52 solar masses. You can see that 1905-21 is one of them, but there's a few other ones which are even more massive, like 1904-26, and then 1909-29. It's also very, very massive, at least for its primary. So all of these could be explained with this kind of model. Also, okay, thank you. So I've included also the spins. You can see that there's very different spins. That's the right-hand column. And in our model, it's very simple to have different explanations. For the binary, you could have very large spins if there has been mass transfer and they tend to synchronize on the plane of the binary. But if the binary has a plane which is inverted with respect to the tertiary, then that could explain spins which are inverted. Once you accrete all this material, you will most likely turn around what the original spin might have been for these black holes. So you could have very, very different results with the spins. So conclusions, basically we need hypercritical accretion to explain these very, very massive black holes in the current stability gap. We need a third massive star which acts basically like a reservoir to store a lot of the material that will later come back to the binary and produce these very large masses. This tertiary star can be produced by this common envelope flow overflow that we have come up with. There's I mentioned about a dozen of gravitational wave sources that may have experienced similar paths. There's a binary, which I didn't mention, but it's on the bottom of this slide, which also has 140 solar mass star and 127 mass star. These are both Wolf-Rayet. They may produce a system similar to what we're talking about with a binary. The question is whether they will be able to grow closer together so that they will eventually merge. Well, the last point is orbital inclination can accommodate for many kinds of spins as observed by LIGO. That's basically it. Thank you very much.
Thank you, Enrique, for your interesting talk.
Thank
Any
you.
questions? Benjamin?
Hi, can you hear me?
Yes, I can hear you.
Okay, perfect. I just have a simple question. Do you have the approximate amount of time it requires from the moment like the stars have been created and the moment they are going to merge into black holes, for example? Do you have an estimation of the time it requires in terms of gigayears?
Yes, well, that depends a lot on the final separation of the inner binary. So basically, you need, in order for the two black holes to merge within a Hubble timescale, you need to be separated not more than a few tenths of solar radii. So you need the two black holes, very, very massive black holes, within, say, 20 solar radii of separation, so that they will merge within a Hubble timescale. So everything that we have observed must have been closer than that, especially because this estimate I'm giving you is for massive black holes, and we have also observed systems with neutron stars or a neutron star and a black hole, and those will radiate the gravitational waves much slower. So they need to be even closer than what I'm saying. In this case, what we can find in our models are orbital separations, which can be a few solar radii, 7, 8, in some cases 15, 16, around there. So though all of those would be merging within a Hubble timescale. So all of those would be candidates in principle.
Okay, thank you. And in your work, so you have an estimation, like, did you provide this estimation? I mean, can we read it somewhere? Because, I mean, I was just, yeah, I'm curious about the time, I mean, this time exactly. I know that you can compute it with the gravitational wave emissions.
Yes.
But so can I find it for your model somewhere in the paper? Or?
Well, the paper is not out yet. That's why it has all these preliminary marks all over. But I don't think we included in this one. But when we do our estimates, we basically take the usual formula for gravitational wave emission, and we assume that it's circular. If these were if this had ellipticity, then it would be even faster. However, since the binary is going through all these common envelopes, most likely the orbit will tend to circularize. So yeah, so that, yeah. But if you need the formula, I can provide you with. No,
it's not especially the formula, it's just the mean time that it's required for the merger.
Yeah, I might have it. I have around 4 talks that I was checking when I prepared this one, and I'm pretty sure the formula is in one of these. So I could just after I finish, I could look it up and send it to you if you want.
Okay, thank you very much.
No
very
problem.
Interested. Thank you.
Thank you. No, Diego is in the paper. He cannot be asking.
No. I'm just saying, like, can you comment on the spins that we expect from this model compared to the spins of other models?
Well, as I was mentioning, so if let's assume that all of them were in the same orbital plane, then you could expect to have very large spins for both. Well, not for both, for the 3 cases. For the primary and secondary black holes, they will most likely be very large because they are doubling their mass. So that means they will grow close. Even if they started with 0 spin after they were formed, they will acquire so much material and so much angular momentum that they will likely grow close to 1. And if they merge with those spins, then the orbital spin will also be aligned with those 2, and it will produce a very, very large positive spin. However, if the binary has an angle or is inverted with respect to the tertiary, then you could accrete angular momentum in the opposite direction. So the orbit and the black hole spins could be misaligned. So in principle, you could do now something that goes to very large values of negative or very close values to 0 in the case you are with a binary orbit, which is, for example, perpendicular to the tertiary.
Vale.
Okay. More questions? No. Thank you.
Okay. Okay. This is the last talk. We have a break of 5 minutes. Please come back at 10:45 Mexico and 17:45. Okay.
See you in 5 minutes. Thank you. Gerardo, Leo, or Rosa, can I try my sharing my screen? Just double check if it looks correct. So can you see me on the presentation correctly?
Yes.
Perfecto.
I can see.
Venga.
Diego, ¿quieres checar que se vea todo bien?
Ya lo hice con Leo o con...
Ah, ok, yo sí me tomé break. Ok, súper.